Imagine you send one HTTP request, but the server quietly treats part of it as two requests, and attackers can sneak a request behind yours. So that sounds really crazy, right? That's HTTP request smuggling. Today, I'll show you why it happens, how you can test it, and we're going to look at some reports as well. So let's get into it. First, let's understand the basics. So when you visit a site, your browser hit a front end, a load balancer, or you can call a reverse proxy like Cloudflare. It is a front end server. So this front end forwards requests to backend app servers. So these are the actual servers that contains code and they process that code. So for performance, the front end reuses a single TCP connection to talk to a backend and sends many HTTP requests one after another. So this is actually implemented to avoid repeated TCP or TLS handshakes, because if you don't implement it, the front end have to use new connection for each HTTP request and to pass it to backends, and for that it takes a lot of CPU power, right? So instead of doing that, there should be one connection and all the HTTP requests will be sent to that one connection, and it also reduces latency. So the flow is like browser, front end, and then backend. Now just to give you a note, all these HTTP requests are HTTP version 1. They're using version 1 protocol. Now you must be thinking, okay, there are a lot of HTTP requests that uses version 2 protocol, and in modern web applications, they use version 2, but in HTTP request smuggling to exploit it, you have to use version 1. So there are still a lot of applications that are using version 1, and even if they're not using it, you can still downgrade that version in a burp suite and test for it. I'll show you how you can do that soon. So, HTTP 1 decides message boundaries in two ways: content length or transfer encoding. These two headers are actually a way of how server is going to read the content in the HTTP request, basically the data that you are passing. Now, you usually pass data in a post request. So when you're testing for HTTP request smuggling, you test it usually in a post request because you have to pass in the data, right? Okay. What happened here is sometimes the front end understands content length and the backend understands transfer encoding, and they might disagree with each other. And what an attacker can do, an attacker can send a request that contains both header and content as well. So the front end is going to read the same content in a different way, and the backend is going to read the same content in a different way. In simple words, an attacker can hide a second request inside the first, and the front end thinks the request is finished while the backend treats the leftover bytes as the new request. Now that new request can be malicious and can be exploited to gain unauthorized access to sensitive data and bypass security controls. If I keep blabbering like this, you're gonna fall asleep. So let's look at multiple practical demos. So to understand how content length and transfer encoding works, I'm going to show you live HTTP request on response so you can understand it better. Okay, so I have this basic request. As you can see, this is a GET request, and actually I picked this request from Web Security Academy. Now I'm just going to send this request, and this is a response. And in the response, you can see the content length, but that's the length of the response, not really important to us. What's really important is this HTTP request. So as you can see, the protocol here currently is version 2, and you can change this. So just go to inspector, go to request attributes, and here you can downgrade the protocol to 1. Now, once this is done, this is how you're actually going to test it actually in real life. Send a request and see, yeah, it is still working. Now, as I said, content length only goes in the post request. You gotta change the HTTP method to post. So through this change request method, you can change it to post and send the request, and you're still getting the same response. But let me give you a reality check. Sometimes you won't get the same response. You'll get 404 not found in real life, but sometimes you'll get 200. Okay, so you have to analyze such behaviors as well. Anyways, so as you can see, this is working for us, and currently the content length is 0, as you can see. So we send this request, and you can see content length is automatically added here, and its value is 0. It's 0 because there is nothing in the request body, right? Let's add something. Let's say hello. Send the request. And we are getting 200, okay? And now the content length is 9. Now you must be thinking, how come it's 9? So let me enable the CRLF characters. Now you can see /r/n says basically space or line breaks, and this is usually hidden, but you can see it once you enable this feature. Now to count it, I'm going to count it from here: 1, 2, 3, 4, 5, 6, and 7, and then 8 and 9. So you are supposed to count these CRLF characters as well. Now you must be thinking, okay, why we are not counting this? Because we don't. Actually, when you're counting, it usually start after that space. So this is the space, and then from here you start counting the actual bytes of data. And that's why the content length is 9. Now if I just increased one more and send the request, this will become 10. So that's a good thing about WebSuite, that it's going to update the content length for you, so you don't have to do too much of manual work. And you can see that it's working. Now in case of transfer encoding, how it works, you gotta provide the transfer encoding header. It's value chunked. And then here how it works. First, you provide the size of the data, that is, let's say 3, and then ABC. So ABC is 3 bytes of data, that's why you're providing 3. Now if there are more bytes, let's say 2, and AB after it. So first goes the size and then the bytes of data, then size again, bytes of data, and once it reaches 0, it means that's the end of it and there are no more data after it. So that's how the server is going to interpret it. It first start reading it, and then when it reaches 0, it understands, okay, that's where it's ending and there is no data. So that's how transfer encoding works. Now that we understand how content length and transfer encoding works, we can easily understand how HTTP request smuggling works. So, as you know that there is some kind of confusion between the front end and the backend server to interpret the data. So there are actually 3 types of confusion. This is my way of saying it. Technically, you call it desync. So there are 3 types of desyncs in HTTP request smuggling. First is CLTE, content length and transfer encoding desync. Second is transfer encoding and content length desync. Third is transfer encoding and transfer encoding desync. Now this video covers content length and transfer encoding and content length. Basically, the front end is using CL and the backend server is using DE. And in the second case, the front end is using TE and the backend server is using CL. Because of these confusions, you can pass through your malicious HTTP request. Let's understand CLTE first with this demo. Okay, now let's exploit CLTE. So in this case, we have this HTTP request and response, and you can see it's a normal GET request. But to exploit CLTE vulnerability, we have to change the HTTP method from get to post, and once it's changed, we can see the content length. Because the post body is the one that carries content, that's why we see the content length header right now and we didn't see it before. Now there is one more thing we want to do, is downgrade the HTTP protocol from 2 to 1. So I already did that, that's why you're seeing it. Now time to add our body here. So let's turn on the CRLF so we can see its spaces and everything. I'll tell you why. So first we're gonna type first 0, another space, and then G, capital G. Why you're typing capital G? Because that's the goal of the lab. It could be any character. We just want to pass the rest of the data to the next request that will be sent by the victim. We want to append our data in the next request of the victim, and the data that we want to append is G character, because that's the goal of this lab. Of course, for testing HTTP request smuggling, you can type any character over here. Okay, now let's send the request again, and we'll see, okay, we're getting 200 okay response, and the content length is upgraded to 6 because there are 6 bytes of data. So we usually don't count this space. We start counting from here: 0/r, 1 byte, 0, which is 1 byte, /r, another byte, /n, another byte. So this makes up to 3 bytes, then 4 byte, 5 bytes, and then 6 bytes. That's why we have 6 written here in content length. Okay, Now, the front-end server is accepting content length. That's why we are getting 200. Okay, everything is fine. But what happens is this G is actually left over. Why it's left over? It's because the backend server is going to accept transfer encoding. Okay, but we haven't added the transfer encoding here yet, so we have to do it. So after this, I'm going to add transfer encoding, and then its value will be chunk. Okay, now turning this on again, and you can see. So the content length is still same, but we have this transfer encoding header, and the backend server is going to take this one to check the data. So how transfer encoding works is the server is going to start reading it, and when it sees 0, it thinks, okay, that's the end of it and there is no more data. Okay, so the front is accepting content length, and it sees, okay, there is 6 bytes of data. Cool, let it pass. And then the backend sees transfer encoding, and it sees, okay, it starts from here, then it sees 0, and it thinks, okay, that's the end of it, there's no more data in it. But the G, this G character is still hanging, right? It's still left over. It's floating in the network chain, or you can see in the request pipeline. So G is hanging. Now what's going to happen is, let's say there is a victim, and the victim is going to send a request as well. So the victim is going to send a normal request, right? The victim, let's capture the request from here. So I'm going to send this to repeater. So this is the victim request. The victim will send a normal request, but the victim will get 403 forbidden unrecognized method G get. Okay, and the victim will think, why this is happening? This is kind of denial of service for the victim. Okay, this is because the G is now appended to the request of the victim. So the G character was hanging over here, right? It was still in the request pipeline. And when the victim sent a normal request, that G got appended over here like this, okay? Just like this. And the attacker, and then the server thought, okay, what the heck is G get? That's not a HTTP method, right? And that's why the victim is getting this 403 forbidden, and this is how HTTP request smuggling works. Cool. Now to solve the lab, you actually have to send a post request. So we can just simply do that. Change the request method to post and send a request. Now there is nothing hanging because that G is already used. That's why you're seeing this. But to exploit it again, I'm just going to send this request again. Cool. G is again hanging in the request pipeline. Server doesn't know what to do with it. Now a normal user sends a post request, and again, that G got appended over here before the post HTTP method, and it becomes gpost, and then the server thinks, okay, what the heck is gpost? Of course, 403 forbidden, because that doesn't exist. Again, denial of service for the victim. I hope this makes sense. Okay, now let's have a look at this report that is reported to HackerOne to understand this better. So this one is reported to Acronis, and HTTP request smuggling on this particular subdomain of Acronis. So the website is vulnerable to HTTP request smuggling, which can be used by an attacker to redirect all users to malicious website. A redirect can be forced by changing the host header using the path/sf, but the website will redirect you to this. To reproduce the attack, use the configuration below. Okay, so this is actually a little complex, but I will try to simplify it for you. Let me scroll down and show you the request, then only you will understand it. So this is the post request. As you can see, the HTTP protocol here as well is 1.1, and then we have transfer encoding chunked, and then we also have content length 4. So this one is CLTE, similar to the demo we saw. First, we can see the content length is 4 bytes. It's because 6, which is 1 byte, 4, 1 byte, and then 2 CRLF characters, /r/n, 2 more bytes, which makes up 4 bytes of data. So the front end is going to see that, it's going to forward the request, but the rest of the request, which is in chunked format, because the backend server is understanding transfer encoding, it's going to take this request. Now you can see the rest of the data in the demo was a character. Now that is a simple version. In this case, the rest of the data that we are trying to smuggle is actually a request. And why it's a request? Because in this case, this attacker is trying to redirect users to the burp collaborator. So basically hiding one request inside another request to smuggle it. Now this is a very real life scenario. As you can see, in the end we also have the 0 to tell the backend server that okay, the request is ending here now. Now these are just the configuration settings for sending a lot of requests. So any normal user who will try to send a request will be eventually redirected to this burp collaborator URL. So to exploit HTTP request smuggling, you're supposed to actually send a lot of this smuggled request and only it's going to work. So we cannot see the bounty in this case, but this one is crazy. You can see how you can chain open redirect here as well in HTTP request smuggling. And of course, whenever a user visits it, the attacker can see in the logs, the HTTP logs, and these logs also contain the user's access token. And through this, the attacker was able to redirect a lot of users to their website. Now this disrupts the normal behavior of the application. Let's say you're just browsing a normal application, and whenever you're sending a request, clicking on something, you're just getting redirected to some weird site that is attacker controlled and you don't know about it, right? And you also know what kind of scripts are hosted there. So yeah, that's pretty crazy. I'll provide this report link in the description. Okay, now let's have a look at another report. So this scenario is TLC, means the front end server is using transfer encoding and the backend server is using content length. Okay, so the application appears to be vulnerable to HTTP request smuggling due to disagreement between front end and backend, which causes desync. And this one is reported to GSA bounty. We have a little description, and then we have the script. This is a script for Turbo Intruder to send as many requests as the attacker wants. So in the previous report, the attacker used, or the researcher used Intruder, but in this case, he's using Turbo Intruder. That's fine, you can use anyone you like. But what's the main interest here is this HTTP request. So this HTTP request, we can see we have another request in it, the original request, right? Now we have both the header here, content length, and transfer encoding, and notice that the content length header value is 4. It means the backend that is prioritizing content length is going to read only 4 bytes, which means 1 byte and then 2 byte and then CRLF characters, another 2 bytes, and end of it. And the rest of this is going to keep hanging in the connection. And because it is hanging and left over, the server is going to interpret it as a new request. So whenever a normal user is going to send a request, this will get appended before that normal request, and that user is going to get redirected to this hopefully 404. Now this doesn't exist, and that's why it's going to get error. But in the host, we have the collaborator URL. So from the following screenshot, you can see that a victim's request was caught, which redirected to a 404 page just as intended. Since this path does not actually exist, in addition, by searching for my burp's collaborator URL, you can see there are 67 instances where the URL is reflected, some within script tags and sources. Okay, so this is kind of similar to previous one, but different form of desync. Now the impact here is, since the JavaScript imports on the page can be determined by the attacker, he can host a malicious domain to steal user data, perform stored cross-site scripting, and deface the web page for the user whose request was poisoned by the desync request. And you can see how critical this is. And this one was rewarded with $750 bounty. And that's a really nice one. I'll provide the link in the description to this one as well. Actually, there are so many reports on HTTP request smuggling. So many are too complex. Hopefully, I might cover those in the future videos as well. But for anyone, for any beginner or even an intermediate to understand how things are working, I think this video is perfect. So in this video, we explored multiple things and hope now you understand what HTTP request smuggling is. I would really suggest you to go and try HTTP request smuggling labs from Postfigure and make notes. Don't ever forget to make notes, okay? So I wanted this video to be fun and educational, not something boring, so hope you enjoyed how I put it. Let me know your thoughts in the comment section. Thanks for watching, and I'll see you in the next one.